morning. I have the pleasure to be a host today and present to you all Mirella Simões Santos. Mirella got her master's degree and her PhD in chemical engineering at the Federal University of Rio de Janeiro, with a collaborative period at MIT. She is currently in her postdoc program at the University of Queensland, Australia. Her work interests include molecular dynamic simulations of confined fluids as electrolyte solutions and anilkane mixtures with carbon dioxide. Also, descriptions of micelle formations by molecular thermodynamics and modeling. She is actually a former atoms researcher, so she is not far from home with this audience. So I'll leave you with Mirella. Welcome, Mirella. Thank you, and you now have the word.
Thank you so much, Amaro, for such a nice introduction. I will just start sharing here my screen to share with you guys the presentation. Just 1 second. Share the screen here. Which screen do you guys see? Do you see the regular PowerPoint presentation or the ones with annotations?
The regular one.
Yeah.
Okay, perfect. So thank you so much again for such a nice invitation. I'm really happy to be here with you guys and to be talking a little bit about the work that I have done, that I'm doing currently here at the University of Queensland, but also some of the work that I did on my previous position at Texas A&M University. So today I'm going to be talking about molecular simulations of confined fluids and applications from oil and gas industry to also to renewable energies. So from my work at Texas A&M University at Economics Group, I was focusing on the oil and gas applications of molecular simulations. And here at the University of Queensland, I'm considering mostly systems related to renewable energies. So I think it is going to be interesting, an interesting combination, and to see how similar approaches can describe problems from such different industries. So the overview for our talk today, we are going to be talking a little bit about some definitions of confined fluids and 3 applications. So the first one would be for CO2 reinjection. The second one, we are analyzing effects of pore sizes and also mineral types for different oil and gas reservoirs. Then the third application, we will be talking a little bit about supercapacitors. I'm going to be giving one extra example and that I think it is interesting, but I think we don't have time to talk much about it, but I still think it is also another good approach to describing confined fluids. And our final remarks. So what are confined fluids? We can define them as a fluid that is subject to a geometric constraint. And this geometric constraint is on a very, very small scale, on an nanoscopic scale. Let me just check. Okay, I was just checking the chat. So for example, we could think of a very small pore where the walls of this pore are very close to each other, and the fluid that is within this pore will be impacted by the presence, its behavior will be impacted by the presence of these walls. So due to this geometric constraint, the molecules will be close enough to the interface with, here in this case that I'm mentioning, the pore walls, and this fluid will sense some difference from its behavior at bulk conditions. And actually, confined fluids, they are present in so many different systems and applications. We can think of confined fluids from, just 1 second here, from living cells, reverse micelles, clatrate hydrates, that I know that is something that a lot of people have been working on at Atoms there in Rio, also for oil and gas reservoirs, and as well as nanofluidic devices. So the last two topics are the ones that I'm going to be talking mostly here today. And confined fluids, as I just mentioned, the properties that they will have when they are within this confined geometry, it will be very different from the ones that we observe at bulk conditions. And this is so because this confinement will impose an inherent inhomogeneity, and this will be reflected both on structural as well as dynamic properties of this fluid that is confined. And so, as I just mentioned, so many processes and systems do have confined fluids, and we know now that the properties of these fluids are going to be different from what we would expect in bulk conditions. So for us to be able to improve different processes and develop different methodologies, we need to understand on the molecular level, what are the phenomena that are involved on this confined system. And this will need to pass through the understanding will need to pass through the development of appropriate methodologies for the determination of transport and thermodynamic properties of confined fluids. So that's what we have been focusing. I have been focusing in my previous position and here at the University of Queensland. And for you guys that were on the lecture last week, I showed this same plot. And so here what we have is a relation between time scale and size scale. So when we think in terms of the confined fluids, we know that there are differences on the interactions and on the behavior of this fluid on the microscopic scale, on the smaller scale. Let me just get the laser point. Do you guys see the laser point here?
Yes, yes, we do.
Okay, perfect. So if we think in terms of this, the microscopic properties of these confined fluids, we would be doing analysis here on this level, from especially using molecular simulation. So we could understand the interactions of the fluid with the walls and how those interactions are affecting the properties of our fluid, right? But this kind of information then can be later used for the development of theories and models that will be applied on larger time and size scales. For example, for the development of chemical thermodynamics theories, and as well as models that can be used for process design and plant design on the topmost level. So this plot here actually was, we put together at my previous group in Qatar, and the three regions, let's say, or relations between time scale and size scale, in red are the ones that we focused back then in Qatar. So if we are thinking here in terms of molecular simulations, we are thinking of a time scale, time scale in nanoseconds, so very short time scales we can consider, and a size scale in the order of nanometers. So those are the restrictions that we would be having in terms of molecular simulations. So switching to the part that we are going to be focusing on oil and gas reservoirs and how molecular dynamic simulations and molecular simulations, they can help us to understand the properties of conflict in those systems. If we think in terms of the recent advances on the recovery of oil and gas reservoirs from shale and tight reservoirs. So those systems, they have been explored much more commonly nowadays, and they present a very large amount of pores that are on the nanometric scale. So pores that are just a few nanometers wide. And those pores are the ones that we know that we would be seeing, we would be expecting to see confinement effects, right? And as we just saw, the properties of this confined fluid, of these fluids within these very small pores, they are going to be very different from what is observed on larger pores. So for us to have a good description and estimation as well of reservoir productions, we should be taking into account as well the confinement effects for the fluids we are interested in describing. And one thing that is, for example, one example on how much the properties of confined fluids can change. Some authors, they have reported that if we have N-octane and decane under confinement, we would be expecting to have a bubble point that would be up to 20 Kelvin lower than what we observe in bulk conditions. So the changes in the properties of these confined fluids, they are considerable. So we should not be neglecting them when we are modeling these complex systems. And the pore size distribution of our, within our oil and gas reservoirs, they are going to be a function of the composition of the reservoir. For example, we know that reservoirs with a high total organic carbon composition would usually have a large amount of very small pores. And here we are going to be, I'm going to be discussing a couple of works that we have done, some considering calcite, others dolomites, silica, different kinds of clays as well. So thinking in terms of CO2 reinjection. So shale and tight reservoirs, they are very favorable and very good sites actually for geological carbon sequestration. So what happens when we have CO2 reinjection or carbon sequestration? We have a CO2 that has been removed from either recycled from the production well or purchased from different sources, let's say, and it is reinjected to our reservoir. And so this technique, it is a good alternative, an important alternative actually, for reducing the carbon footprint of the oil and gas industry. So the CO2 that would be injected would be trapped within this oil and gas reservoir. But not only an effect of trapping this reservoir would be happening, but as well as having when the hydrocarbon that is within this reservoir being displaced due to the injection of the CO2. So this is seen as enhanced oil and gas recovery process as well. So we would be enhancing the recovery of hydrocarbons from this reservoir through the injection of CO2. Oh, sorry. Just 1 second. Okay, apologies for that. So if we, for us to be able to describe this, the phenomena that is involved on CO2 reinjection, we should be able to understand exactly what is happening on the molecular level. So here we are using molecular simulations to give us some insights on what is happening through CO2 reinjection. And so this work was done at Texas A&M University, and because we were in the Middle East, in Qatar, the reservoirs that we have there, they are mostly composed by calcite. So in this study here, we consider calcite as our mineral pore walls. And so what we did was to consider that our pores, they would be described as slit pores. So we would have 2 layers of this mineral. at a certain distance from each other. And we would have our fluid within these two layers. Let me just check the chat here. Okay, perfect. So, and we perform then molecular dynamic simulations for these systems. We use GROMAX software, and we consider an NVT ensemble. So our pore size, our pore height would be kept constant. And as we were focusing on CO2 reinjection, we considered that in this system here, this work that I'm presenting now, that we had CO2 and some different alkanes confined within our pore. And to describe the CO2 and alkanes, we use the Trapp force field, and for calcite, the Schiao force field. And here we are going to be studying the effect of the presence of CO2 within this pore and that contain alkane initially, as well as effects of the concentration of CO2, of different lengths of the alkanes, as temperature and pore size. So the first goal of this work was to see and analyze what was the impact of the CO2 adsorption into a pore containing alkanes. So here I have one example. A pore, so here is the calcite surfaces. We have a constant height here of our pore, and we have pure methane at a certain density. And what we see when, after simulating the system is that the density distribution, so here as a function of the z direction, so it's reflected, it is directly related with this picture here. We see that the density of methane close to the calcite surface is much higher than what it is in the middle of the pore. And so this is expected. But what happens when we insert an equimolar amount of CO2 into this pore is that CO2 will be displacing the methane that was initially adsorbed close to the calcite surface, and will be pushing this methane towards the middle of the pore. So what we see now for the density profile of methane is that methane is not adsorbed so strongly on the calcite surface, and it was pushed towards the middle of the pore. So we can see that. Let me just remove the pointer. Let me see if I can click, maybe with this one. Just 1 second, I'm having a little trouble here with, okay, now it is. So you can click on the video with the pointer or the pen. So, okay, let's see the video. So we have calcite, we have methane initially close to the calcite surface, and we have CO2 here in the middle. And what we see is that CO2 starts to be the component that is closer to the calcite surface in a larger amount as well. So to describe these changes in the amount of CO2 and methane adsorbed on these calcite surfaces, we define the variable that we call the equilibrium local ratio. So that it simply gives us what is the fraction between the amount of CO2 and the amount of alkane on this adsorbed layer. So the adsorbed layer was defined as a function of the density profiles for a region where we have changes on the density of the component that we are analyzing, less than 2%. So initially, if I go back here quickly, so if we think here of this region, when we start to see changes in density that are less than 2%, so we have a density a bit more constant, we have the end of this dense layer that we are considering here. So going back. Here we have one example where we have some simulations, some results for a mixture of CO2 and methane, again in the calcite nanopore. This time the height of the pore is 4 nanometers and the temperature 375 Kelvin. And we have this equilibrium local ratio for different densities. Let me get the laser pointer again. For different densities and also for different compositions of the mixture. So 33% of CO2 and methane and so on. So what we see is that for the higher the density, the average density inside the pore, we have a higher equilibrium local ratio. So we have a higher amount of CO2 relating to alkane ratio on this surface. And so this shows us that the CO2 has a higher absorption affinity towards the calcite surface when compared to methane. And this is attributed to the strong polar interactions between CO2 and the calcite surface. And so, for example, this kind of behavior has been seen experimentally. There has been some work on limestone, pink limestone, that has shown when having both CO2 and methane being adsorbed to this pink limestone, we have a higher selectivity for CO2 adsorption. And this is the same qualitative behavior that we are observing here. We also analyzed effects of temperature for this system. And temperature is a very important parameter when we are analyzing this kind of competition between the adsorption of different components. In this case, we have here again a mixture of CO2 and methane, equimolar mixture, same pore height, and we have the equilibrium local ratio as a function of density, but for different values of temperature. And at higher densities and at lower temperatures, so this region here, what we see is that the CO2 composition in the adsorption layer is much higher than that of methane in the same layer. And this, of course, indicates a higher selectivity for CO2, and this is directly related again with the strong polar interactions between CO2 and the calcite. And this will dominate, especially when we have low temperatures where the thermal energy is lower. And so we have here in detail how the mass density profiles for CO2, the continuous lines, and methane, the dashed lines, for 3 different temperatures. They are changing as they are changing. So here we would have the calcite surface. So here is going towards the middle of the pore. And we see that we have a higher adsorption of CO2. Here is it's clearer to see, sorry. We have a higher amount of CO2 being adsorbed on the surface when we have the lower temperature. And finally, for this, this work, what we have also analyzed was the effects of the pore sizes. And so here we have 3 different pore sizes and keeping the same information about temperature and mole fraction of CO2 and methane. And we have again continuous line for CO2 and dashed line for methane. And we have 3 different average densities inside our pore and 3 different pore sizes. And we see, as we are increasing the density, the average density inside the pore, we see a larger amount of both components being adsorbed on the calcite surface. And as we are increasing the pore height, or the pore width, sorry, what we see is that there is a certain limit to the amount of CO2 being absorbed on the calcite surface. So for the larger pore here, I have 8 nanometers. For the different average densities inside the pore, it looks like we are reaching a certain plateau in terms of CO2 absorbed into the calcite surface. And this is so because CO2 absorbs preferentially over the calcium sites of the calcite surface. Sorry, okay, I got my mouse back. So what we have here is an example of the calcite surface. So we have the carbonate and the calcium sites. So CO2 would be absorbing within these yellow sites. And we calculated using the density profiles, what would be the local density of CO2 for different average densities for the smaller pore. Let me see, okay. So for the smaller pore, and we have here local density of CO2 on the surface. So local density would be number of molecules over area. And we compare this constant line here, this red line, it is the number of calcium sites per area as well. So we see that as we are increasing the average density, the number of CO2 being absorbed on this calcite surface is tending to be the value of the calcium sites. So here I just presented structural properties of this fluid and structural analysis and equilibrium analysis for how different alkanes, here I just presented methane, but on our paper we also analyzed butane and octane. So here we were only focusing on equilibrium and structural properties of alkanes within a mineral pore, within calcite, and how they impact, how the presence of CO2 impacts the behavior of this fluid. But transport properties, they are also very important, especially on the oil and gas industry. And one work that was we did and published the end of last year in collaboration with UCL. So we worked with Maria Apostolopoulou and Alberto Istriolo. Also from the Qatar group, we worked with Mohammed Hamza on this project. And here what happens is that we know that transfer properties, they are very important. And we also know that there are some state-of-the-art methodologies that have been developed to couple imaging data that gives us information about composition and pore size distribution of rock sample to generate some realistic pore networks and that can resemble the reservoir rock that we intend to model. And then mesoscale simulations can be performed to describe those systems. But those mesoscale simulations, they are limited by the quality of the input information that we have to describe that system. And so here, one of the things that we are proposing is to couple information from atomistic simulations that we do know that we can provide an accurate understanding of transport mechanisms in confinement, but trying to couple this kind of information to upscaling to a larger time and length scales that is required because we have because of the limitations that we have due to computational time using atomistic simulations. So here, what we had proposed was to a novel 3D stochastic approach that uses input from atomistic molecular dynamics simulations to kinetic Monte Carlo methods that can describe the diffusion of a certain component within different minerals, let's say. So the minerals that we considered here are silica, alumina, magnesium oxide, calcite, and muscovite. And one of the things that is very important, or that I think it is relevant, is that this coupling of different methodologies gives us and makes us able to obtain a library of models that could describe the diffusion of a certain fluid within different materials. So let me just pass to the next one. So as I just mentioned, what we have initially is information from molecular dynamics simulations, equilibrium molecular dynamics simulations of the fluid of interest, that in this work is methane, supercritical methane. And we use this information as an input to the kinetic Monte Carlo framework, modeling framework. So we consider slit pores again that would resemble the reservoirs that we are interested. And initially we considered pores of 5 nanometers of height. So, so from this information, we can obtain, for example, information about the different regions of within this pore. Do you guys remember the plots that I just showed you, that we see an adsorbed region? So here we would be calling regions 1 and 3. They are very close to the surface of the mineral. And we know that in the middle of our pore, we have a bulk-like region, so that we are calling it region 2 here. And so this kind of information is used as input for our kinetic Monte Carlo approach. And then we can have a prediction of the behavior of the property that we are interested, that is the diffusivity of methane, as a function of the pore size. And without all the very, very high computational cost that would require us if we were to obtain this relation here through only molecular simulations. Okay. And I don't think I added here a slide with the information about the simulation details, but here methane was described as united atoms, and calcite was described with the same force field that I just mentioned, Shell force field, and all the other minerals, they were described through the clay FF force field. So to characterize the structure of the adsorbed methane on each pore surface, we have here plotted the surface density of methane for the 5 different minerals that we considered. So we have here in the Y and X direction, and we have the density of methane. So we see that for most of the systems, we do have a very structured organization of this methane within the mineral surface, but we do also see that there are very different patterns and behaviors that we see for each one of these systems, for each one of these minerals. And so we consider same temperature, same pore size, and same average density of methane within each one of these systems. And one of the things, so just going back here, one of the things that we obtain from these initial molecular dynamics simulations are the density profiles for methane within the different minerals. So we consider 5 nanometers pores, and we also compare the density profiles for the systems for 10 nanometer pores. And what we saw was that for these conditions, the density, the width of the dense layer, of the adsorbed layer, and the amount of molecules adsorbed in each one of these layers didn't change as a function of the pore size. The change was smaller than 10%. actually smaller than 5%. So this made possible to consider for the next step when coupling with the kinetic Monte Carlo approach that the width of this adsorbed layer and the number of atoms adsorbed as a function of the area of our mineral would be constant for the different pore sizes. So as a comparison, what we have here is for the different minerals and for the different regions. So just remembering the region 2, the orange ones are the middle of the pore. So we see when we compare for the bulk density, here we have diffusion coefficients as a function of different minerals, and we have 5 nanometer pore and we have 10 nanometer pore, and we see that we have in the middle of the pore almost bulk-like behavior for the different minerals in both pore sizes. Calcite has a unique behavior, let's say, because of such a strong interaction that it has with the fluid. It causes the density in the middle of the pore for these pore sizes to be lower than what we would expect in bulk conditions for the same system. That's why we have a higher diffusion coefficient for methane in the middle of the calcite pores in this case. And another thing that we can see is that silica, for all the components, we have at the adsorbed layer a much lower value for the self-diffusion coefficient. So the methane that is adsorbed close to the mineral surfaces, it is behaving very differently from the middle of the pore, and it has its mobility reduced. So that information, the 5 nanometer pores, was used as an input for the kinetic Monte Carlo methodology. And for 35 different pore widths for each one of the minerals, we will obtain the self-diffusion coefficient for methane. So the sphere, the circles, sorry, they are these 35 points for each one of the minerals. I'll be showing the others in a second. And we have, again, our dotted line for describing the bulk density. And we have axes here that they describe the data from MD simulations. So we use the 5 nanometers, and the 10 nanometers was not used as an input for the system for the kinetic Monte Carlo algorithm. And so what we see is that as the slit pore is increasing, so now we have pores of much higher size, much higher width than we had before when we were using the atomistic description with molecular dynamic simulations. And we see that as we are increasing the pore width, the diffusion of methane is tending to go to the bulk value. And we have the same for all of the minerals. And here we have also for calcite one extra point for 25 nanometers. So this point here was calculated separately through molecular dynamic simulation. We have a very small deviation from what is predicted through this model. And we also for muscovite. So I think that from this part, what we get is that this proposed methodology seems to be very efficient to combine information from the atomistic side, from molecular dynamic simulations and kinetic Monte Carlo simulations. And this can be useful for us to generate a kind of a library that we would have diffusivity of gases or of fluids as a function of the pore chemistry. So for different minerals or different materials that this gas would be confined to. And this would be relevant for so many different applications. For example, from the prediction of hydrocarbon transport in shale rocks, as we have been talking mostly, and to the optimization of catalysis and different applications. So this is the oil and gas part. It was the largest one, so don't worry, it's not half of my talk. I already passed that point. And now I would like to change a little bit from the oil and gas industry to what I am interested now, that is renewable energies. So the work that I'm doing here, the main goal is to apply computational strategies to understand the mechanism of charge and discharge of nanostructured supercapacitors to guide the enhancement of their performance. So there are some keywords here, not necessarily the ones I put in, in purple, but if we look here, okay, nanostructured and okay, mechanisms, it kind of brings us a little bit already to some of the feelings that we would have for the previous projects that I just showed. So what are supercapacitors? So supercapacitors, as a general definition, we can say that they are devices that store electrical energy by the physical adsorption of counter ions in the electrostatic double layers within high surface area porous electrodes. So these electrodes and this adsorption of the ions, they are mostly happening within systems or within orders of magnitude that are very small, just a few nanometers, one electrode from the other. And or either that we have, for example, porous electrodes that we have very small pores where the ions or of the fluid that we are considering, they are interacting on a different way with the electrodes. So if we consider very long electrodes with very thin double layers, we can model these systems very easily with some simple approximations like linear RC transmission line. But the possibility of nonlinear response due to either a very large applied voltage to the surfaces of our electrodes, and also for when we have very narrow pores, again, going back to the confinement, that this would lead to very thick double layers. These systems, they do not have not received, sorry, as much attention as they should have. So the current goal for this project is to calculate local diffusion coefficients to nanostructure heterogeneous systems and show how the local diffusion coefficients in electrolytes vary with electrode structure, voltage, and type of electrolytes. So here we have not only the effects of confinement, but also very strong effect of the interactions of the ions of the electrolytes with the electrodes. And why local diffusion coefficients are important for us, or are relevant for us. This property per se is very interesting for us because when we have higher diffusion coefficients, it is related with having higher power densities, and this can give us the kind of information that we need to have some insights on proposed structures and changes on possible structures or combinations of electrolytes with structures that will increase the performance of those supercapacitors. Okay, so here I have just a couple of slides on application to supercapacitors. So we have a large group working on this topic at the moment. And I think in a couple of months, we're going to have some publications from this topic. So I can discuss more then when we have them, and would be happy to do it. So here I have one example that it is using a coarse-grained force field for the validation of different approaches. So what we are doing is to propose some different methodologies for the calculation of these transport properties when we have such a highly correlated fluid, such an ionic liquid, and also considering that we have confinement effects. So on this model here, we are considering, as I just said, the coarse-grained force field for imine BF4, and I'm presenting here non-charged electrodes. So we have graphene electrodes. Here the distance between my electrodes is 10 nanometers, and we also analyze when we have charged electrodes as well. So here on the group, we are considering not only coarse-grained models for force fields for the ionic liquid. Those we are using mostly for developing theories and validation of theories. But we are also using atomistic and polarizable force fields for describing the ionic liquids. They are computationally more expensive than this one. That's why we are using the coarse-grained force field for validating the theories before applying to the very slow system, let's say. And when we have no charges on our graphene surface, and we have our ionic liquid within our pore, here we are considering 350 Kelvin on the simulations, and I'm using molecular dynamics simulations and GROMACS for performing the simulations. What we have is a behavior very similar to what we were discussing a couple of slides back. So we have both the anion and the cation being absorbed on the surface of our electrodes. And as we don't have a charge on either electrode, we have a very symmetrical profile here. And so we could say again that we have a region 1, a region 2, and a region 3, right? So we have the formation of the electrical double layer and the confinement effects to be taken into account when trying to describe the systems. And the pore size also influences on the transfer property of the ions. And so here, when we do apply a charge on the electrode surfaces, so what we have here is the density profiles for the cation and for the anion. So the anion is mostly absorbed on this side. So the right-hand side electrode is positively charged, and the left-hand side electrode is negatively charged. And we do see that we have here, we have density in terms of ions per volume. So we can compare directly because these two cation and anion, they do have different molar masses. So, but here we can compare directly. So we see that we have closer to the electrode positively charged, a larger amount of anions adsorbed when compared to the amount of cations that are adsorbed on the negatively charged electrode. And there are effects both from both steric effects as well as different interactions with of the different ions. And if we calculate the self-diffusion coefficients for the different regions, we again see that in the middle of the pore we have a higher self-diffusion coefficient of the ions, both cation and anion, and a much lower self-diffusion coefficient within the adsorbed layer for both cases. So, okay, that's my extra example. But just going back here to the application to supercapacitors, what we have been mostly focusing now at the moment, so is developing different theories to describe these transfer properties of within supercapacitors when we do have very highly correlated fluids such as an ionic liquid, as well as we are considering different effects of different surfaces and corrugations on the electrode materials. So this is, in my opinion, a very interesting topic, and would be happy to talk more about it in another opportunity. And the very last slide of examples that I have is another project that I'm working at the moment that uses a lot of what I did during my master's here there at PECI. And so, okay, we have been talking about confined fluids and confinement effects for 45 minutes now. And another system that I think is very interesting, very relevant is when we think of confinement, not only like between pores, like two sheets, one close to the other, but also on a different geometry. A reverse micelle is an example of that. The confined fluid, that is the water that is inside this reverse micelle, that is isolated here, is confined on a spherical dimension, or a spherical medium. I don't know the right word to describe that, but how do we calculate and how do we describe the behavior of this water when the restrictions are not only on one direction, like that direction, but are on a restricted on a spherical way. So that's something that I have been working now, and I think it's a very interesting topic and would be happy to discuss in the future about it. And so our final remarks or a summary of this talk are that the properties of inhomogeneous fluids, they can differ largely from the ones that we observe at both conditions. And besides that, the methodologies that are focused to describe homogeneous fluid, they cannot be applied to describe confined fluids, and that's why it is so important for us to have methodologies that are able to predict the properties of confined fluids. And in terms of the oil and gas reservoir analysis that I've mentioned, an atomistic description of the reservoir rocks enables a deeper understanding of the interactions between the fluid and minerals. And also that confinement effects cannot be neglected as they influence largely the properties and behavior of fluids, from both hydrocarbon reservoirs to supercapacitors, as I showed here. And that just as a really final conclusion from here is that molecular simulations that are very important for accurate prediction of thermodynamic properties and transport properties, and also is very useful aid for process design. So before I finish, I would like to acknowledge the funding agencies, both from Qatar and also the computational centers from Texas A&M at Qatar, Advanced Scientific Computing, Pulsing, and NCI from Australia. And I would like to thank both groups from Economical Group in Doha, Qatar. So we have a few people missing here. Professor Marcel Castillo, for example, Mohamed Hamza, Moa Selam as well. But this is the most recent picture that I had. And also would like to thank the Bernhard Group here in Australia. So this is Professor Deborah Bernhard. This is from our end of the year celebration that we had. So thank you very much for both groups for receiving me and for such a great work that we have been doing together. And finally, I would like to thank Atoms. And here I have a picture from the second end of the year conference or symposium from Atoms. And thank you so much, guys, for the opportunity. And I would be very happy to receive any questions, and we can talk more about any other topics. Thank you
so much, Mirella, for this lovely presentation, and always being so open to talk to us. I'm actually a huge fan of your work. And now we have time for questions. If anyone wants to ask a question and don't want to ask in English, you can ask in Portuguese, because she's Brazilian, she'll understand. And also you can write at the chat. Thank you.
Hi, Mirella. Can you see me?
Hi. Yes.
First of all, thank you very, very much for such a nice talking. I think I was not part of the Atoms when you were there, but I do know well your work. I do know you. You left such a great impact on our group, so thank you very much for that too. I have two quick questions here. I would like to start the questions. You were talking, you showed us several diffusion results in different pore sizes, right? You were talking about regions 1, 2, and 3, close to the walls and in the bulk, let's say bulk. My question is, how did you establish these regions? Did you consider a homogeneous slab, for instance, in the middle of the pore to calculate diffusion there? How did you handle this? This is my question. Did you use a slab or something like that?
So one of the ways that we had defined, because it's a bit ambiguous. So because usually you have like more than one peak. So if we had only one peak, we could define, okay, only this peak. But what you see is one or two or three even peaks close to the surface. So for the first work that we were considering, actually for the others too, we considered that we were checking how much the density was changing from the surface towards the middle of the pore, and when this change of density was smaller than a certain amount that we defined, I think it was 2% that we defined, we would say, okay, it stops here, this dense layer. But for example, when we have, I didn't present here, but there is a different approach that we have used to describe perpendicular self-diffusion coefficients, and that approach specifically needs you to have a linear density profile, so a region with a linear density profile. So for that methodology that we applied on a different work, we consider a much thinner region to describe this density, because for us to have to describe this diffusion, because for us to have a linear density profile, it should be like going up on the slope or something like that. So it changed when we had to change the methodology that we were using. Yes.
Okay, I got it. Thank you. The other question, well, it's about the second part of our presentation. I imagine you imposed the electoral fields in these simulations, or didn't you use electoral fields?
For the last part?
Yes, or not?
No, so that is specifically what we consider was constant charge to describe the electrodes.
Oh,
but
okay.
We have also, yes, so that for validating the theories we are developing, because it's faster and it just removes some extra terms that we would have to take into account. But when we are describing work systems that we want to be closer to what is observed experimentally, let's say, we are considering a constant potential applied to the electrodes. So that's a different way of modeling the electrodes that we also consider, yes.
Okay, I was wondering if you could consider constant charges, or if you could impose on electoral fields, if there are any difference in this approach.
Yes, no, actually it is expected to have some differences on the behavior of the ionic liquids if you are considering the constant charges or constant potential on the cell. So it is a very important topic. So I think my suggestion would be, if you're trying to describe, for example, experimental values, I would go with constant potential simulations. Yes.
Great. Thank you, Mirella. Thank you for such a nice talking.
Welcome. You're welcome.
Thank you.
Hi, Mirella. How are you? This is Luis.
Oh, Luis. Hi. How are you?
I'm fine.
Luis was one of the authors of the first paper that I presented here.
Thank you so much for this presentation. I'm loving to see you again. It's nice to see that you're continuing this beautiful work on confined fluids. I don't have any questions, actually, just to comment this. I'm very happy to see you here. Actually, I have one minor question. So for this work with supercapacitors, that you impose some charge on the graphene layer, the graphite wall, do you freeze this wall? I mean, you consider they are the atoms are restraining their positions, because if you impose this charge and you have some fluctuations in this wall, I would say this electrical field would be much more challenging to calculate. Is that correct?
Yes, no, I agree. So for the constant charge, we do fix the walls, and the methodology that we have been using for constant potential, let me think. Yes, it is also fixed, but I know that there are some issues when we are applying some of the theories that we have been using, especially when we have non-equilibrium simulations. So yes, no, yes, I agree that there would be some some issues, let's say, that should be addressed as well.
Thank you, Mirella. Nice to see you.
Nice to see you, and nice to hear you. I didn't see you, but nice to see you, Luis.
Yeah, that's right. That's right.
Actually, Professor Richard Elliott has a question. Mirella, if you want to read it. If you don't.
Let me see.
Yeah.
You
I
can
have a
ask.
couple of questions. He can ask? Okay.
Yeah, anybody who wants to read it can look at the chat window. So it's basically a couple of questions about the cutoff treatment in the confined fluid. I noticed on the slide it says that the cutoff was 1 nanometer and something about particle mesh E-wall being used. So the first question, just wanted to clarify, was particle mesh E-wall applied to the dispersion forces then, the Lennard-Jones types forces?
Can you repeat, please?
So was the particle mesh E-wall applied to the Lennard-Jones types forces or to the point charges on the?
No, to the Coulombic charges.
Oh, to the Coulombic charges. So then you just use a sharp cutoff on the. So that was not force cutoff or cut and shifted or anything. It was just cut at 1 nanometer.
I don't remember exactly now. I'm not sure, Luis. Do you remember exactly for that system?
Yeah, so Richard, usually, hi Richard, how are you?
Hi, how are you?
Yeah, so we used, basically the cutoff radius is for the Lennard-Jones part, and then we use PME, actually PPPME, I think, for the electrostatic forces. And then in this approach, we need to establish also a cutoff radius, but this cutoff radius for PME has not the same meaning as for the Lennard-Jones part, because you do the Evold summation anyway. So it's just the way you stop the reciprocal space, I think. So it's not the same meaning as the cutoff radius for the Lennard-Jones part, but I think we fixed the same 1 nanometer. The other thing is that the wall is made as thick as possible to avoid any spurious interactions between images across the wall.
So
I answered you, sorry.
Oh, okay. So the cutoff was only applied to the Coulombic interactions?
No, actually, the cutoff was applied to the Lennard-Jones part, and the Coulombic interactions for the Coulombic interactions we used PME.
Okay. So when you cut the Lennard-Jones, did you shift the potential? Did you cut and shift, or did you?
No, just use the pure cutoff. Yes, we didn't shift the potential.
And doesn't that interfere with the energy conservation and the dynamics?
For dynamic, I don't think this is quite so important for dynamics. I mean, for Monte Carlo simulations, this would be very important, correct? Because then you measure the energy. But for the molecular dynamics, we only need the derivatives. So I don't think this is so much important. But anyway, you're right. We could use a shift potential.
Okay. I think I understand now. Thanks.
Thank you, Luis.
Can I make questions?
Yes, of course, Fred.
First of all, first question is, your lipstick looks like the same color as the atoms behind you. Is it on purpose?
No, it was not, but when I checked the video, I was like, okay, it was a good decision.
For the first part of the talk, we know that maybe water inside the port changed a lot the structure of the fluid inside. Did you test this?
So not on that work that I have mentioned, we haven't analyzed that effect, but we did analyze it also with Muhammad Hamza, the effect of water on the when we have CO2 and different alkanes in calcite and on silica as well. So what we see is that water adsorbs preferentially as well on the calcite surface. So we have a displacement and the silica surface. So we have a displacement of the behavior that we had observed previously. And also we had a collaboration with Imperial College where the absorption of methane and CO2 on calcite was considered analyzed when we had water present within the calcite pores as well, and how it influences the absorption on those systems. But we haven't published those two yet, but okay. I'll let you know when we have.
It may cause a lot of different properties on the adsorption, no?
Mm-hmm.
Okay.
Yes.
That's why I wonder. In all your calculation with the first paper with Louise if I understood, is NVT calculation, is it?
Yes, yes, it
so
is.
You don't know if this concentration inside the pore, which phase it should be in equilibrium, like if it's reasonable or not, this concentration and this composition inside the pore.
Mm-hmm.
So it's maybe interesting to put together not only NVT calculation, but also grand canonical calculation to see if the composition inside the pore is reasonable compared with the bulk.
Yes, no, I agree, Fred.
Okay. And I'm curious about your last work. Are you back to supercapacitors and super?
Yes. So a lot of the things that I saw there with like the Poisson-Boltzmann equation and mean field approaches. So now they are very useful for me.
Nice. But are you planning to finish some paper that is still open?
Yes, no, definitely. Actually, the one on differential capacitance, I've been applying a way more recent approach to, and using also molecular dynamic simulations to compare some of the results obtained. And I think that chapter will probably be out before the impedance one. So yes.
Yeah, you can also you can also mix them, you know, like you calculate in one scale the interaction between ions and surface, and in the other scale use Poisson-Boltzmann to change the scale. It may be interesting.
Yes, no, I agree. I think it would be very, very nice.
Okay, thank you, Mirella.
Thank you, Fred.
Fred, can you hear me?
Yes.
Can I add something on the discussion on the density inside the pore? We have we have done some absorption calculations using direct coexistence method, like the pore at one side and the bulk phase at the other, and they seem pretty reasonable. So we chose actually these densities, these first densities, actually running bulk simulations with 24 megapascal with reasonable pressure for oil reservoirs. And then we chose this density to confine the fluid. So it's pretty reasonable for natural gas at least.
Thanks, Luis. Okay. I believe.
I see one question from Carla here, asking if I intend to study the influence of some soil specificities, such as surface defects or exposition of specific crystalline planes on the preferential adsorption of CO2 on calcite. So from my side, I will not be doing that kind of analysis. I'm not sure if back in Qatar they will be considering this the effects of defects and different planes. But I think would be something interesting. But I can check with him. Luis, are you guys studying this thing in Unicamp? Take into account this, but for supercapacitors, we are considering some defects and some corrugated surfaces, and so on the different application, we are working on that now. But for CO2 absorption on calcite, I'm not sure if anyone is working on that at the moment.
We have done. We didn't do any work on this right now, but we intend to do as soon as possible.
It's a very, very good point. Thank you.
Mirella, I have one last question. I know we are bothering you a lot, but my question is regarding Professor Elliott's second question, because he mentioned that Professor Bruno Horta has written that PME cannot be applied to inhomogeneous fluids, but we do use it a lot. So I would like to know if you or Professor Luis could say something about it, because I wonder about it too in my simulations, and I know it cannot be applied to inhomogeneous fluids, but I think it's not a closed topic already. I don't know what to do. I don't know what are my other options. So if you could, or Professor Luis could mention something about it, I would appreciate.
Luis, do you mind getting this one?
I don't mind, but I'm not sure I know the answer.
Me neither. We can get to.
Sorry about that.
It's a tricky point or question,
yes,
but in terms of that.
Yes, actually, I need to say that I'm not aware of this Latz-Eval method. Is it the same as the particle mesh or not? It's just another way to, or is it a specific method? I don't know. If someone can answer this to me.
It's in a 2019 paper of Professor Horta that he sent me after I made a presentation in this seminar group, and then I can dig it up for you if you want. If you send me an email, I'll send you the paper, or you could contact Professor Horta. What we've been working on is basically we encountered this problem when we were simulating water vapor interfaces, liquid to vapor interfaces of water with surfactant. And what we ended up having to do just to get something self-consistent was make our cutoffs something like 25 angstroms, which made the simulation times really, really painful. So it wasn't a long-term solution. So our new answer is to develop a method for retuning the force field so that you can use force switching or force cutoff, so a zero force cutoff, and so that you have a continuous force at least. So then you can just take the trap potential, let's say, and figure out what's the right epsilon and sigma that will still give you the same bulk properties as the trap potential, but have a smooth cutoff at something like 2.5 or 3.
Bruno used to be here in the seminar, but I haven't seen him.
Yeah, he's unfortunately not here today because he had another appointment.
Okay.
But thank you, Professor Luis, Professor Elliott. I know it's and Mirella. I know it's a tricky question, but I was wondering if you had any ideas how to solve this problem. We have any further questions? Let's finish. We have another question, Mirella.
Yes,
So
yes.
Gabrielle is asking, Mirella, you were talking about renewable energy, and it got to me thinking, can molecular simulation be applied in the process of biodiesel production? I know it wasn't the focus of these presentations, but I got curious about it.
Would it be in terms of, for example, the reaction process or something like that? If it is in terms of reactions, we have some limitations. We do have reacts force fields, but the time scale that we would be able to describe would be much smaller. But maybe I'm not sure what other, for example, maybe separation processes or something that I'm not sure. Let me think. Could be too. That's a good point, actually. I'm trying to think of a way that it could be used, maybe to predict the properties of some of the components, but I'm not sure, because one of the limitations is in terms of the time scale and the size scale that we can simulate or using molecular dynamics or molecular simulations in general.
Thank you so much, Mirella. Actually, gonna have to wrap it up because we're past the time. But I wanna thank you again for this lovely presentation. And we want to invite everyone to the next seminar. Please use to share the screen so we can invite everybody. Just a second. So for the next seminar, we're gonna have Fernando. Actually, we are in a series of TBAs, throwback atoms. Fernando actually is also a former atoms researcher, so please join us for our next seminar, June 4th at noon here in Brazil. Thank you so much, everybody, and we'll see you next.
Thank you, Mirella.
Thank you,
Bye-bye.
guys. Bye-bye.
Bye-bye.